Right. So before we get started, I want to mention we're going to have a quiz on Wednesday. It'll be over the section 7.1 that we just finished up. So over the identities and the trig substitution stuff that we talked about right at the end of class last time. So let's see if we can write down a couple more examples with the trig substitution stuff that we mentioned last time. And then get into some new stuff today. So let's just make up a couple. So let's say you're wanting to rewrite, let's say, square root of 16 minus x squared, and we wanted to rewrite it without the radical by doing a trig substitution. So remember again, we have those three Pythagorean identities, and really only two of them matter for this one. We have that sine squared plus cosine squared equals 1. We've got the 1 plus tangent squared equals secant squared. And those are the two that we need. Typically, we'll rearrange these two to see the other two forms that we want. So if I do 1 minus sine squared theta, we get cosine squared. And if we do secant squared theta minus 1, we get tangent squared. And the whole idea behind this trig substitution stuff is to do some pattern recognition, right? The idea is that here I see a sum of constant plus a variable squared. Here I've got constant minus a variable squared. Here we've got variable squared minus a constant. And if we can do the substitution appropriately, we get perfect squares. And again, the whole goal of this exercise is to try to get rid of the radical by doing a substitution with a trig function. The good thing, if I can write it as a single perfect square, because I take the square root of it, they'll cancel each other out. That's our whole goal, right? So first, let's see if we can recognize which of the three patterns we want to use. Yeah, so we want notice we've got constant minus variable in this case, right? That fits the 1 minus sine squared equals cosine squared, correct? Okay. The only other thing we need to worry about then is that thing, right? Notice the identity is 1 minus sine squared, not 16 minus sine squared, right? So sine is the correct substitution, but what constant do we need to work with in here so that I can factor that 16 off and see a 1 when we're done? A 4, right? I need to worry about doing the square root of that 16, right? So if we make x equal 4 sine theta, we plug that in, we get 16 minus 16 sine squared. We can factor out the 16 and get 1 minus sine squared, which is exactly what we wanted because we replaced that with cosine squared. And now what does that simplify to? 4 cosine. Good. Technically, again, it's 4 times absolute value of cosine. But anytime that you ever make this type of a substitution, you're assuming that the theta is in the first quadrant, so your trig function will be positive. You don't have to worry about making absolute value. But remember, again, technically, if you do the square root of a square, there should be absolute value bars here. We don't worry about them in trig substitutions because, again, we're going to assume the quantity is positive, so we don't have to worry about it. This seems like a weird exercise to do because you're not seeing the reason why we do it. And the bad news is that you won't see why you do it until you take second semester calculus. So there's a darn good reason why we want that square root to go away, though. Just that we don't actually see it until later. Let's do another one. What if you had square root of, let's say, 36x squared plus 25? Again, first thing you want to do is figure out which pattern it fits. Which pattern does it fit? Good, the tangent squared plus 1 pattern, right? Because again, we've got variable squared plus constant, right? Well, the only one that has a plus sign in it is the tangent squared one, right? So the substitution we know we want to make is x equals something times tangent of theta. We just have to figure out what the something is for the constant to be adjusted, right? That's the thing we need to figure out is what the something is, right? Okay. So notice over here, what was it that we needed to factor out in this first example? What do we need to factor out? The 16, right? We need to factor out the 16. To factor out the constant. So in this example, I need to factor out a 25, right? That's the thing I'm going to need to factor out, so it's left with a 1. So what constant do I need to put in here with my x in order to make this 25 when I simplify it? Because I need to be able to factor out the 25. So what constant do we need to put in with the x so that I end up with a 25 when I'm done? A 5 whole squared will give me the 25, but I also still have that 36 on there. Be 5 over 6. Good, exactly right. I need the 5 so that when I square it, I get 25. I need the 6 so that when I square it, it cancels out the 36. Okay, so I got to not only put the 5 in so that we can factor out the 25, I also got to put that 6 in the denominator so I get that 36 off of there. Does that make sense? So then when we make the substitution, I'll go through the steps here. So we'll have 36 times 25 over 36 tangent squared theta plus 25. Your 36's go away. You can pop the 25 out in front. And tangent squared plus 1 then is what? Secant squared. And now when you do the square root, you get five secant. Good. Yep. It's okay. Not too bad once you get the hang of it. It really is pattern recognition, and there really are just the 3 patterns. Okay, it really is. If you've got constant minus variable squared, you'll use sine. If you've got constant plus variable squared, you'll use tangent. If you've got variable squared minus constant, you'll use secant. It really is just a pattern recognition on that. It's okay. All right. Well, let's talk about some new stuff then, because that sounds like fun, doesn't it? No? Rather not talk about new stuff? All right. So let's go on to coming up with some new trig identities, because that sounds like a lot of fun. Ryan, you don't want to do one. You don't have to take one if you don't want to do one. All right. So in this section, we're going to come up with what we refer to as the addition and subtraction formulas for sine and for cosine and for tangent. All right. So rather than me just telling you what they are and going on with life, I hate doing that. I'd rather tell you where it comes from. Plus, this gives us a chance to review some trig relationships. So, try to do this step by step. try to make the steps as small as possible so that we can get down to the formula that we want. So first off, let me talk about why we care about such formulas. Because what you would really like to happen, do not write this down because it's not true. What you would really like to happen is that, right? That would be the nicest thing to have happen, right? Okay. Unfortunately, this is false. Okay, this doesn't work. Let's see why. Okay. For example, what is sine of pi equal to? 0, right? What's sine of pi over 2 equal to? 1. Is this equal to this? No, this is 0 and this is 2, right? Okay. So the sign does not distribute over a plus sign. Now remember, in saying distribute implies that we're talking about multiplication, which is not what we mean when we write sine of something, right? Sine is a function, right? Okay. Sine of something, right? So we don't distribute anything with functions, right? Just like square roots don't break up over sums, exponents don't distribute over sums. We would not expect sine to distribute over sums. However, there are situations in which we would like to be able to rewrite the sum of two things or a difference of two things inside of a sine or inside of a cosine. So that's what we're going to go for today, is see if we can figure out a way to rewrite the sum. All right. So let's look at our picture and see what we're going for with this. This should be a pretty straightforward question. This angle is alpha. This angle is beta here. This problem is asking you what's the measure of DAG in terms of alpha and beta. This one's alpha and this one's beta. The big one is alpha plus beta, right? Okay, cool. All right, that wasn't a trick question. I've got beta stacked on top of alpha, right? So for example, if we've done problems with that, right? If this is 20, this is 30, the whole thing would be 50. You just have letters rather than numbers in there. All right. You're also told in this setup that this entire distance is 1, right? Tells you that AD is 1. And here is the AE that's referred to in the next question. Do you see the big right triangle ADE? So here's A plus B. Let me draw it off to the side so I don't have to keep writing on that particular picture. You've got right triangle. This side is 1, and this angle is alpha plus beta. The problem's asking you, what is this side in terms of alpha plus beta, or in terms of alpha and beta? Well, I have an angle and I have a hypotenuse, and I'm looking for the opposite, or the adjacent side. What trig function are we talking about? Cosine, right? Cosine of alpha plus beta should be adjacent over hypotenuse, right? The hypotenuse is 1, so this is the length of AE. Okay, so before we go on to the next stuff here, let me just talk about why we care. Okay, remember, we're trying to figure out addition formulas for sine and cosine. We're doing cosine first, just because that was what I typed up first in this handout. Nothing special about doing cosine first. But notice I've got my one length in this particular picture, I've got one length, and it's equal to cosine of alpha plus beta. I want to also get this length in terms of another expression, and then we're going to have an identity. That's the idea. Okay? So the rest of this is coming up with another way to write this, and then we'll set the two pieces equal to each other. That's how we're doing this. Okay? All right, so what does the next thing say? In terms of beta, what is AF and DF? All right, so in this case, erase that part. We're looking at the triangle ADF here, right? That big long piece. So again, the angle we have is beta, and the hypotenuse of that triangle is 1. So let's do AF first, only because that's what's listed first in the question. Relative to beta, AF is which side of the right triangle? Adjacent. So we want the adjacent. We have the hypotenuse, so again we'll use cosine, right? So your AF will be cosine of beta. What about DF? Sine of beta. Good. Because DF is the opposite side, right? DF is this opposite side here. So far, so good? Okay. What's the next question here? What's the relationship between alpha and angle BDF? That's an interesting question. Let me scroll back up to my picture. It wants to know, how is this angle here, alpha, related with this angle way up here? Let's go through it step by step. That's a right triangle. So if this is alpha, that angle right there is going to be, this is a right angle. If that's alpha, this one's going to be beta. Yeah, ignore the beta part. Let's just look at this triangle. Yeah, this is the complement, right? It's 90 minus alpha. All right. Now, what's this one that's going to be right directly across from it? If this is 90 minus alpha, this one's going to be 90 minus alpha. They're vertical angles, right? Those are always equal. Okay. Well, if this is 90 minus alpha, and that's a right angle, what's that going to be? Alpha. Yeah, let's go back to alpha again. All right, so they're equal. They're equal to one another. Everybody see it? All right. Keep going here. So it says using 3 and 4. So the answers that we got to 3 and the answers that we got to 4. What is the length of BF in terms of alpha and beta? All right. So what do we have? We've got, let me just redraw the triangle here. I'll draw it this way. At BF, you got the right angle at D. We said this was alpha up here, right? DF we said was sine of beta. That was what we said from part 3. Now it's asking what's BF in terms of alpha and beta. All right, so I've got this adjacent side. I want to know this opposite side. Tangent, right? So tangent of alpha is BF over sine of beta, right? Tangent of alpha is opposite over adjacent. So your BF will be tangent of alpha sine of beta. So far, so good? All right. So the next part says, what do we need to use? It says we need to use 3 and 5 to give us a B. That's a different one. However, do we know what AF is? Let me go back up here. Do we know the whole length of AF, this part? The AF was cosine of beta. Good. And do we know what BF is here? We just found it. So how can I figure out what AB is? See? So I know the whole thing, and I know this little bit. Just subtract them, right? Good. So our AB is going to be the whole thing AF minus the little part BF, right? AF was cosine of beta. That was the whole thing. BF is tangent alpha sine of beta. Yeah. Now we're almost done. All right. So it says using, what part did it say? Using 2, what's AB in terms of alpha and beta? All right, so AE was this part here, right? You agree? And now it wants to know what AB is in terms of alpha and beta, right? Okay. So notice we've got the little triangle now. We have alpha here, right? We know that this side is cosine of alpha plus beta. Can we figure out what this side is? That's what it's asking us to do. It's cosine, right? It's the hypotenuse, isn't it? Okay. So you should have cosine of alpha equals cosine of alpha plus beta over whatever the length of AB is. Right? You're doing adjacent over hypotenuse. Do we agree? So going back over here, AB should be cosine of alpha plus beta over cosine of alpha. Hey, I think we now have 2 things equal to each other, don't we? Or 2 things that are equal to the same thing, I should say. So they're equal to each other. So combining our 6 and our 7, we have cosine of alpha plus beta over cosine of alpha is cosine beta minus tangent alpha sine beta. But we said the whole goal of this was to get to a sum formula for cosine. What happens when we multiply both sides by cosine of alpha? Well, I get cosine alpha, cosine beta in the first term. What happens when I take cosine alpha times tangent alpha? What do you end up with? Just sine of alpha, right? So tangent is sine over cosine, so your cosines will cancel. There's your sum formula for cosine. That was exciting. Ta-da! We got one. We also have the difference formula for cosine now as well. Notice something here. When you do cosine of alpha plus beta, you get cosine alpha, cosine beta, sine alpha, sine beta. But notice the sign in the middle flips. So what do you think would happen if I change the plus sign to a minus sign? What do you think would happen? If I change the plus sign to a minus sign here, what do you think would happen? Be a plus sign over there. And think about why. If I have a minus beta here, I can rewrite that as a plus a negative beta. You'd have cosine of opposite beta and sine of opposite beta. But remember from your even odd identities, the cosine of negative x is the same thing as cosine x, because it's an even function. Sine of negative x is negative sine of x, so it'll end up flipping your sign. You're flipping your SIG in. Negative sign to a positive sign. Okay. All right. So before we do the next one and get the sum formula for sine, let's see how we would use this. Let me scroll to the part B. Part B here in that third, what is that, the third page? Third page? Yeah. There we go. On the third page there. Let's see how we would use this for cosine of 165 degrees. Or negative 165 degrees will turn out to be the same thing anyway. Okay. So here's the idea. 165, not one that we know the exact value for, right? Which I don't think it is it? No. Okay. However, we can rewrite negative 165 as negative 45. I'll write it this way, plus a negative 120 this way. Do we know what cosine of 45 is? Yeah. Do we know what cosine of 120 is? Yeah. We know both of those, right? So here's how you can use the formula. You're going to write it as cosine negative 45 degrees times cosine of negative 120 degrees. Then it's minus in the middle, and do the exact same thing for the sines. I could have got rid of the negative to start with, but I just wanted to use the formula the way it was written. So the formula again, when you have a sum, is cosine, cosine, minus sine, sine. And just as kind of a helpful hint, anytime you're trying to rewrite these with the sum or the difference formula, you're always going to use 45 degrees or pi over 4 as one of your angles. They're all rigged that way for the sum formulas and the difference formulas. But now we should be able to figure these out. Our reference angle will be 45 degrees. Cosine of 45 is what? Square root of 2 over 2. Negative 45 degrees is in quadrant 4, so cosine will be, good. It'd be positive, good. So it'll be the root 2 over 2. Reference angle for 120 is 60. Cosine of 60 is 1/2. Yep. Cosine of 60 is 1/2. Negative 120 is over in quadrant 3, so it'll be negative. Good. Sine of 45 is root 2 over 2. We're in quadrant 4, though, so it'll be negative. Again, reference angle for 120 is 60. Sine of 60 is root 3 over 2. Negative 120 degrees, though, is over in quadrant 3. Was negative. Now, at this point, I don't really care if you simplify them, but if I did simplify it, you'd have, I can put a negative out in front and have root 2 plus root 6 all over 4. I can factor out a negative sign and put it in front of the fraction. Again, I do not care if you do this last step. You can leave it in that previous step. That tells me you know how to do the problem. The rest of it's arithmetic, and I don't care. I don't care for purposes of what we're doing. Generally speaking, I do care about the arithmetic. That's not the focus of the problem. Is okay? All right, so again, using the sum formula here is a matter of rewriting the angle you're given as a sum or a difference of two angles that you know. I could have written this as 15 minus 180, but that doesn't help me. Right? It's not very useful to me because I don't know what the cosine of 15 is.
I was going to ask if you could like replace those with, say, like negative 90 degrees and 75 degrees or something like that.
You can, except that I don't know what cosine of 75 is either. So I can do it with other angles. It's just a matter of I need to make sure I know what those are. So for example, you could have done 30 and 1 to 35. Those two I do know what the cosine are. It's usually though it's just easier to think about it as use 45 or use pi over 4 as one of them and then write the other one and it'll work out one thing, you know. Easier way. At least that's the easier way to think about it in my brain. So questions on that one? We're gonna do more of them, but is this one okay for what we're trying to do? All right, let's see if we can get the other formula, and then we'll write down our conclusion there. So let's go back to page 2. Same setup. Notice, and I told you that AD and AC were equal to 1 in the diagram, but we didn't use AC at all for the previous one. I thought we used it in this one. So we end up using what the length of AC is for this one. All right. Answer to the first question is the same answer to the first question of the previous one, right? DAG is still alpha plus beta, same idea. Okay. All right. Now we're going to start focusing on some different sides, though. Notice in the previous one, we were doing the sum formula for cosine, and we looked at the adjacent side, AE, for angle alpha plus beta. This one's looking for the opposite side. So what's the length of DE going to be in terms of alpha plus beta in this case? Good, sine of alpha plus beta. That's exactly right. Again, this still has length 1, doesn't it? So that's still the same hypotenuse, and we're interested in this opposite side over here, right? Okay. Now it says, what is DF in terms of beta? Now, looking at this right triangle, AFD. Here's beta. AF is which side relative to beta? Adjacent, and we have hypotenuse, so we're going to use cosine. Good. So our DF here will be, or that's our DF. I was looking at the AF. DF is the opposite side. Sorry, my bad. I was looking at the AF. That is the adjacent. DF is the one we want. That's the opposite side, so it'll be sine. Good. My apologies. So DF is sine of beta. I think we had that in the previous part anyway, didn't we? All right, what's next? Well, that's the same question as we had before. What's the relationship between alpha and angle BDF? They're equal again, right? Because we have alpha, and then this is 90 minus alpha. That's 90 minus alpha, so way up there is just alpha again. So now we've got, let me draw this picture. I'll rotate it a little bit. Here is BFD. Yeah. We know this angle is alpha. And we know this side is sine of beta. Now I was looking at the hypotenuse of that right triangle. So relative to alpha, this side is the adjacent. That's the hypotenuse. So we want to use which function? I have adjacent and I want hypotenuse. Cosine, right? So cosine of alpha is going to equal what? Over whatever the BD is, right? So BD is sine of beta over cosine of alpha. We okay so far? Okay. Now on the front side just means the previous page. From number 6, what was the length of AB? We already did this one a minute ago. Okay, so it was AF minus the BF, which was equal to what? Let me scroll back up to number 6. What did we get? Cosine beta minus tan alpha sine beta. So that was the length of AB. And now it wants the length of BE. So we got alpha here. This was AB, and this is E. And it wants this side. So we're given the hypotenuse, and we want the opposite. So we want to use sine. So sine of alpha is BE over that mess, right? I'll just write it over AB. So your BE is sine of alpha time. I'm just going to distribute it. We got sine alpha cosine of beta. And then minus the product. Something's not going right here. Sine alpha tangent alpha sine beta. All right. I just distributed the sine alpha through that to those different pieces here. All right. So, what do we have? 2 tells us something about DE, which is the whole length of the thing. And we just figured out what? BE? Right? We figured out DE, and we just figured out BE. Is that right? Okay. 5 told us something about BD. BD is sine beta over cosine alpha. Yeah. Okay. So let's see if we can put all this stuff together. All right. Such a mess, isn't it? All right. So anyway, pardon me. we've got, where was BE? Let's go back up to the top here. Try again. This whole length of DE is sine of alpha plus beta, correct? So sine of alpha plus beta is the length of DE. We agree? Okay. DE is the same thing as BE plus BD. So let's see if we can put these pieces together. We've got sine of alpha cosine beta, sine alpha tangent alpha sine beta, and then a plus, what is that, sine beta cosine alpha over cosine alpha? Yeah? All right, what do we got now? All right, so notice that our tangent alpha piece here is what? That is sine of alpha over cosine of alpha. And we got a sine beta there. Oh, no. You agree with that? Do you see a common factor in this term and this term? See a common factor? I've got sine beta over cosine alpha here and one there. So I can factor that out of those two terms. I know it's messy. We're almost done. And then you never have to do it again. Oops. So I'm going to factor out sine beta over cosine alpha. I'm going to rearrange the terms. I'm going to leave a 1 here. When I factor this piece out here that I'm putting the little dashed circle around, what are you left with? When I pull out the sine beta over cosine alpha out of that second term, what are you left with?
Sine alpha cosine beta.
So when I factor this part out, what's here? Yeah, it's sine squared alpha, isn't it? What can I replace that with? Cosine squared alpha. And then what happens? What can you do now for a final step? Yeah, cancel a cosine out, can't you? Okay. All right. Shoo, we got to the end. Took a little bit to get there. That one was uglier than the cosine one, wasn't it? All right, so let's write it down. So that was, notice sine of alpha plus beta will keep the same sign, right? It has the plus sign in the middle, but your trig functions are mixed. Okay. So when you write down the sum formula and difference formula for sine, we'll have sine alpha cosine beta plus or minus sine beta cosine alpha. So notice it's the reason why I'm writing the formula this way. Plus here is plus here. Minus here is minus here. So you get mixed sine and cosine. Keep the same plus or minus in the inside, in the middle. Okay. However, for cosine, you keep the same function, but you flip the sign in the middle. Oops. This is what I expect you to remember. I'm not going to make you reproduce those other things. I just really, really hate writing down a formula and not at least giving you an idea of where it comes from. And that reviewed some trig stuff anyway. A lot of messy algebra in that last little bit, but it reviewed some trig stuff to make sure we could reinforce those things. And no, I would not expect you to come up with that on your own, because that would be crazy. So far, so good? All right, let's see if we can do a couple more examples with this before we go and do some more tomorrow. Let's look at part A here that I skipped last time. Again, the idea here is, do you know what sine of 75 is off the top of your head? No. But can I rewrite 75 in terms of two angles that you do know the sine and cosine of? What can we use? 45 and 30. Always try to use 45 or pi over 4. Okay? So this is sine of 30 plus 45. Now using our formula, what are we going to have here? We're just going to rewrite it right now, and then we'll do the values, yeah. So using the formula, we'll have sine of 30 times 45, and then is it plus or minus in the middle? Plus, it's the same sign in the middle, good. And then sine of 45 cosine of 30. Now let's get the values. Sine of 30 degrees is 1/2. Cosine of 45 is 1 over 2 over 2 over 2. Sine of 45 is good. And cosine of 30 is 3 over 2. In the end. I mean, you can simplify it if you really, really want to. Do you think I care if you simplify it? No, you'd be correct. I do not care. Let's do one with radians before we go, since we have 2 minutes. Sine of negative 11 pi over 12. Well, one thing you could do before even starting this is using your even-odd identities. What can I do with that negative sign using the even-odd identity? What can I do with the negative sign for sine? Does it go away or does it come out in front? Is sine an even function or an odd function? So what do we do with the negative sign? Good, exactly right. It goes out in front, good. Probably easier to do it that way to start with, right? All right, so now let's think of rewriting 11 pi over 12 as a sum or a difference of two angles that you know. What angle did I tell you to always use? Yeah, pi over 4, 45. Pi over 4 is how many twelfths? For 3 twelfths. So we still need 8 twelfths, or 8 over 12 reduces to 8 and 12 have a common factor of 4, so it reduces to 2/3. Yeah, 2 pi over 3. Good. So pi over 4 plus 2 pi over 3. And now we can use our sum formula again. It'll be sine of pi over 4 cosine of 2 pi over 3 plus sine of 2 pi over 3 cosine of 2 pi over 4. I can talk. And then you know the exact values for those angles, so you would be able to simplify that. Notice I kept the minus sign all the way out in front since we took the negative out for the even odd identity. I'll let you finish that up since we are officially out of time. We'll do more examples. This isn't all the examples we're going to do. We'll do more of these on Wednesday. But also remember, we'll have a quiz on Wednesday. Be a couple of identities to verify and proof substitution on it, like we did at the beginning of class today. All right? Have a good one, everybody. See you on Wednesday. I hope I didn't numb the brain too much with the triangles.